And being far away, spacetime becomes more and more flat, right? Because you recover the good vacuum that you had before without branes. Now, in these non-SUSY strings, there is no such vacuum. So what happens when you go far away from the brane? Turns out we found that you cannot get far away from the brane, right? There is a limit to how far away you can get.
The guest of today's podcast is Dr. Ivano Basile. He is a theoretical physicist at the Max Planck Institute, and he works on non-supersymmetric string theories, supersymmetry breaking, and recently, breaking of global symmetries. So let's talk to Dr. Basile about his work in physics and listen to what he has to say. So Dr. Basile, welcome to the podcast.
Hi, thank you so much for the invitation.
So before we talk about anything else, what kind of projects are you working on nowadays?
Oh, well, many things, but so I think mostly two types of projects, I would say. So one is more formal, theoretical. Let's say the overarching goal of my research is to try to answer the question of whether string theory is the only possible quantum completion of gravity. This is the problem of string universality, it's called. And I have been looking at this problem from many perspectives, using various techniques, anomalies, black hole physics, scattering amplitudes, various types of things, both from the string theory point of view, what people call the top-down approach, and the swampland point of view, which is the so-called bottom-up approach, where you are agnostic regarding the actual theory that you're working with, and you try to sort of reconstruct it. This is the more formal side of my research nowadays. And then I have some ideas in the more phenomenological side of things. I've been studying some types of models that arise in non-supersymmetric strings, right? Some models of cosmology, which take the form of our universe living on some sort of bubble expanding in a bigger universe. And lately, I've been trying to let's say I have a suspicion that there are some potential problems with these models, not theoretical problems, but problems for make them realistic. And so I'm trying to develop this research and see if indeed these kinds of models can work or not.
Right. Okay. So before we talk about the projects that you have worked on and the projects that you are working on in detail, can you tell me that how did you get interested in theoretical physics?
Oh, that's a great question. So I think I got really hooked on this idea when I was a teenager, say about 15, 16 years old, which is essentially half my life at this point, which is kind of scary to think about. But I remember I was, self-studying some stuff in mathematics and physics. I was always very interested in mathematics since I was a kid. Right? And then I started seeing some more advanced ideas in physics and math, and I got super interested. And then at some point, I found the documentary by Brian Greene, right, the one on his first book, I think, The Elegant Universe, and I was completely fascinated by it. Then I got eventually into topics like relativistic quantum field theory and general relativity and other things that are extremely beautiful in many ways, and I decided that I wanted to do theoretical physics.
Right. So you said that you watched the documentary by Brian Greene, The Elegant Universe. So does it mean that you were interested in string theory from a very early age?
Yes, I was. Then I sort of lost interest for a while as I was going through my undergrad and bachelor's and master's degrees, mostly because the environment was essentially free of any input from string theory. There were no people working on it that I was in contact with, except eventually who would have become my advisor, Augusto Sagnotti. And I was feeling like there was not a lot of activity, Of course, I was completely wrong, but it was just my biased impression within the context I was in, right? So I started getting interested in many other things like quantum information, condensed matter physics, other things, other topics in theoretical physics. Eventually, I found my way back to string theory and quantum gravity in general, and I never left since.
So you said that since there was not a lot of activity regarding string theory in your undergrad, you kind of lost interest for a while. But was it also because it was discouraged to do string theory, or was that not the case?
So I have heard stories about some students being more actively discouraged, but personally I never went through any of that. So for me it was just a passive, let's say, absence of stringy ideas floating around in discussions and courses and so on, except at the very end when I was already familiar with some basic string theory and related topics, but there was an actual course that was held at the Scuola Normale toward the end of my degree, and by the end of the course, we were two people attending, just to give you the scope of the environment that was there at the time. Then eventually in the subsequent years, many more students started attending those courses. A few more people were hired, not necessarily in string theory proper, but in related topics, and so the environment in there became a bit more active, which it still is to this day. And then, of course, unbeknownst to me, in other parts of Italy, there were more active string theory groups and courses happening. And then I discovered that only after the fact, let's say.
Right. So who taught this course?
So the one I attended was taught by my advisor,
Hmm.
Professor Sagnotti, who is a prominent figure in the field. And in the later, in subsequent years, the course was split in various parts, taught by various people, some of whom were invited from other places in Italy, actually. So it was a bit more varied in scope.
So when you transitioned from condensed matter physics to string theory, what topics did you need to catch up on to start working on string theory? And the second question is that did your background in condensed matter ever help you in in your research in string theory?
Well, so when I say that I went into condensed matter, what I meant was that I started a master's thesis in that topic. Right, it was about the tensor networks and the quantum Hall effect. But I always tried to keep my background as broad as possible, and as I was saying before, I had already started studying things related to quantum gravity, string theory, and related topics before getting into these more condensed matter direction, which means that I didn't really have to catch up on things that I had left out of my study endeavors. Of course, I did have to catch up on material required for the thesis itself, which eventually, the second thesis that I undertook was about non-supersymmetric strings, and of course, I had to learn a bunch of background material for that. But I didn't feel like I was behind, if that makes sense.
Right.
And as for the second question, I do think that delving a bit deeper into condensed matter did help my understanding and research even today, because I think theoretical physics especially is whole, it's one. The rules of the game are essentially the same. The principles, the ideas, stuff like the renormalization group, right? How conformal field theories work. All these things are universal. Of course, there are some aspects of quantum gravity that make it special, right? But they don't make it special in a way that changes the fundamental principles. At least that's what we are finding so far. It introduces new ideas like holography, right? Or black hole physics. But I think having a broader view of theoretical physics beyond just particle physics and related developments is very helpful, because even just the way we understand quantum field theory in a modern sense, let's say in the past 50 years or so, is very heavily influenced by condensed matter physics. Even the very recent developments on generalized symmetries, anomalies, topological aspects of these systems is very heavily influenced by condensed matter physics. So I think it's really helpful to have a broader, understanding of these topics.
Right. Okay. So I'm going to ask you a question, and I think that's knowing what I know. I think that's I mean the answer to that question doesn't exist in our understanding, but I'm still going to ask you that question, so you can try your best to answer it to an audience who is non-expert, or an audience that is composed of students. So if I ask you what is string theory, how would you respond?
So I was asked this question not too long ago by a similar kind of audience, and the way I started answering was, it's a quantum mechanical theory that includes gravity. That's I think how I would begin answering.
Mm-hmm.
Then I was asked, okay, what's the definition? And then I said, we don't know, because we have no complete definition. Let's say, I would say we are much closer to a fully satisfactory definition of relativistic quantum field theory than we are for string theory. Nevertheless, we have very good reasons to believe that there is a theory there. We have good control of various limits, or various sectors, various parts of the theory, and they fit together in remarkable ways. And they fit together in a rigid way, in the sense that, as far as we can tell, the theory is unique, and there is no way of changing it in any way. Of course, you can change the particular configurations, states, the parts of limits of the theory that you look at, but the theory itself seems to be unique and rigid. So the fact that all these bits and pieces of the puzzles appear to fit together, as far as we can tell, is a non-trivial statement, right? Because it could have been otherwise. We couldn't have manipulated these pieces to fit together forcibly, right? Either they fit or they don't, and they seem to fit. So we have very good reasons to believe that there is a theory there, and this theory has, among various properties, these two properties. It's a quantum mechanical theory that has low energy limits that include general relativity coupled to other quantum fields. So it reduces to relativistic effective field theory at low energies, and it's complete. It never breaks down. So all the observables are meaningful at all energy scales, all kinematic regimes of the theory, and it seems to be unique. Right, it has no parameters, nothing you can change. Let's say. So this is how I would begin answering the question. But hopefully, it's vaguely helpful.
So let me come from a mindset of the a person who learned string theory from popular science, and that person may say that, well, I've heard about like type 2 strings, heterotic strings. So how can you say that this is unique?
Very good, very good. So actually, this kind of lingo of different string theories is even kind of present in actual research papers of recent date, which is kind of misleading in my opinion to some extent. Of course, when researchers know what they're talking about, it's fine. But I guess my broader conceptual point is that these things you listed are some pieces of the theory. There are some limits, some sectors, right, that describe part of the theory, not the full thing, and they are not distinct because there are some processes or limits that you can take in various, in the regime, the space of physical regimes of the theory, where you can get from one to the other, right? They seem to be connected, all these limits. That's why people think since the 90s, mid 90s or so, that string theory is unique, and these sectors are only apparently distinct, right? Because perhaps maybe you do some weakly interacting physics in one of these corners, and you never see that you can describe the physics of the opposite corner when you go to when the interactions are strong, for example. So yeah, there are several sectors of the theory, and we are far from understanding all of them. But yeah, that's my take on it.
Sure. So you said that you have these connections between different sectors. So you are you're referring to these type 2A, type 2B as different sectors, right?
Yes.
So can we go start from any sector and use these connections and go to any other sector?
So this is let's say what we expect. This is the expectation based on what we know. In some cases, we have very strong evidence that we can do this, right? For example, the connections between, let's say, type 1 and type 1 string theory and a certain kind of heterotic string theory that is realized when a particular, let's say, coupling that characterizes the strength of interactions is, goes from weak to strong, and what is weak in one description becomes strong in the other description. Now you could object to this by telling me, hey, didn't you just say that there are no parameters you can change? And the reason why this still makes sense is that these couplings are not constants parameters, right? They are moduli in this case. They are expectation values of dynamical fields or emergent fields in some low energy limit, let's say. So they are dynamical degrees of freedom and there are there is a space of vacuum configurations of these degrees of freedom, and you can choose where you sit in the space. So it's not a space of parameters, right? It's a space of configurations, let's say. And by moving in the space, you can connect between these different descriptions. So in some of them, we have very strong evidence that these connections exist. In some other cases, we don't even know if there are connections. So we are, the expectation is the theory is ultimately unique for various reasons, but we have to look into this more. More research is needed to settle this conclusively.
So you said that you said about the string coupling constant that it is related to the expectation value of the field. I mean, you're talking about the dilaton, right? So,
Yes.
I mean, and I agree that this is the usual answer that people give, and which is correct. But I don't know if you saw this recent article by Thomas Banks where he said that coupling constant should not be taken as the expectation value of the dilaton. Do you know where he's coming from when he says
So
that?
I did take a look at that paper, and I feel like, so I mean, as far as I remember the story, was that he was claiming that these kinds of quantities should be considered parameters rather than you know
Moduli.
some moduli, let's say. I mean that they are moduli. I think it's fair to say, regardless, but whether they count as parameters or not. And so the general gist, if I remember correctly, so don't quote me on this, I could be wrong, but was that ultimately what is fixed is the value at infinity, right? Because the whatever non-perturbative full definition of the theory should be, we expect that involves the sort of the holographic boundary, so to speak. And the values of stuff at infinity, including moduli, if any, defines a super selection sector of the theory, because no fluctuations of anything can ever touch the boundary at infinity, right? It takes a sort of infinite energy, to change, and there are no let's say overlaps between states in different sectors. Um, and I think this is correct. But then I would say if you don't want to say that these things are moduli in the sense that they parameterize vacuua of the theory, and you don't want to say that because maybe what is a vacuum in some effective field theory, is a notion that ceases to make sense in the full description, which only involves the boundary at infinity. Okay, but then we can say that these values label superselection sectors of the theory rather than parameters. So my understanding of what a parameter is in a physical theory is that it's outside of the theory, right? It's a knob that you can change, and then the theory changes. But our understanding of stuff like the value of the dilaton at infinity whenever there is a dilaton is that it labels one of the sectors of the Hilbert space, right? It's a superselection sector. So even if it doesn't survive as a bona fide modulus in the effective field theory sense, to me, it still doesn't count as a parameter. It counts as a label for a superselection sector. That would be my take.
Sure. Okay, I see. Okay, so you work on string phenomenology, and string phenomenology has had a lot of relevant questions over the years. So in this decade, I mean, we are at the mid of 2020s. So in this decade, or in this year, what do you think are the major problems in string phenomenology that people are working on?
Yeah, that's a very, very, very good question. I'm not sure I'm the best candidate to answer that, since my work in the more phenomenological side of things is somewhat limited. But let's see. I think we I think it would be better, like let's say people focus a lot on the deSitter vacuum, right? Or lack thereof, or let's say, are there any deSitter vacuum in the string landscape, right? This is a huge question, obviously, but the extent to which this is a phenomenological question, I'm not completely sure of, because yes, dark energy exists. It's positive. It's very small relative to the Planck scale. Is it constant, right? Why should we live in a deSitter configuration? It's not clear to me, right? So of course it's a simple model of dark energy, no question about that. But we learned that in a complete quantum gravity context, what looks like a simple model from the effective field theory point of view may be far from simple from the point of view of the complete theory. So if there are actual deSitter vacua, so configurations with a cosmological constant, where dark energy is constant, is not clear. If there are, they are probably metastable, which, whatever, doesn't really impact the consistency insofar as perhaps there is at least one stable configuration somewhere. But whether this has to do with phenomenology has to be seen, because maybe, dark energy in our universe is not actually constant, right? Maybe. So I would say, to go toward answering your question, which is, very difficult to answer, but I think a great question is, what is the nature of dark energy, right? Or what kinds of dark energy can emerge in string theory, right? Which is a bit broader than are there deSitter vacuum, right? So there may or may not be deSitter vacua in the landscape. If there are, they're probably metastable. But could there be other kinds of configurations that produce some kind of dark energy which is still realistic, right? This is my
Right.
question number one for string phenomenology. Question number two would be, are there configurations that are, where something called separation of scales occurs? So the separation of scales is the idea that that there is a consistent description of physics from the point of view of a low energy observer, right? And it looks like, low energy observers in realistic models of our universe see some sort of four-dimensional effective field theory, right, of some kind. Includes maybe the standard model, stuff like that. Which means that whatever scale governs new physics that goes beyond this kind of phenomena should be undetectably small for at least the kind of experiments that we have been doing, right? So the separation of scales is the separation between the scales where low energy physics takes place, for example, dark energy, or the Hubble scale, and the scale of new physics that that tells you, hey, the full story is not just some four-dimensional effective field theory. This is separation of scales in a broad context. Now, I I think there have been spectacular developments in the recent years toward finding constructions that are of this type, right? That satisfy scale separation. So it would be great to understand, is it conclusively possible? How far can you push it? Can you make it arbitrarily big, or there are some limits to it? So there are these kinds of questions, and relatedly, sorry.
Don't you think that in the recent years there has been more work on forbidding scale separation in a lot of contexts? Like
Absolutely, yeah, that's true. But this is why I said, this is why I was talking about the extent to which it can be achieved, right? Because it seems like there are some obstructions toward the strongest kind of scale separation, which is parametric scale separation, right? Which means that you can make the separation between the scales arbitrarily big, right? There's an infinite sequence of constructions where this ratio diverges, right? Now that seems to be problematic, yes. There are some, ideas that seem to go around it, but then these ideas have potential problems, and so there are debates and so on. So personally, I don't really believe in parametric scale separation, to be honest, but there seem to be, works that are convincing to me, at least, not completely bulletproof, but somewhat convincing, that there are extents of scale separation that are numerically reasonable, right? Stuff like 10, ratios of scales that are 10 to some number with 2 or 3 digits, right? Which I would say, for a realistic model, we may not need parametric scale separation in the end, right? I mean, people have been doing perturbative calculations with the standard model for decades, and the couplings in the standard model do not go below 10 to the minus 2. So it's not that big of a deal, is one thing for phenomenology.
Can I come back to what you just said? You said that you don't believe in parametric scale separations.
Yeah.
Okay, and do you have any reason for that?
Yeah, so this particular idea is not extremely well supported, I would say, but the reason why I am more toward the side of it's impossible is mostly because it would seem to violate the idea that the landscape of inequivalent EFTs is finite, right? So as far as we know, every time we can answer the question whether some subset of the string landscape is finite, or even the potentially broader question, quantum gravity landscape of a certain type, whether it's finite, every time it seems like the answer is yes, right? There are some exceptions that are, unclear whether they are excluded or not, but they're not conclusively included. So there seems to be this idea that the landscape of inequivalent EFTs is finite, which doesn't mean that the set of vacuum is finite. It obviously isn't, but the inequivalent EFTs, right? And the parametric scale separation would exhibit infinite sequences of EFTs which are inequivalent. So
Okay.
that would go against that, and then of course at least in the context of EFTs of this type that have stable anti-deSitter vacua, then you can ask a similar question, presumably in a holographic setting with some conformal field theory question, right? You can ask, is there an infinite sequence of conformal field theories such and such, where this gap, whatever corresponds to the gap of scales in anti-deSitter is arbitrarily big. And every time people have looked for this kinds of stuff, they always failed for very subtle reasons. And then maybe people would give a counter argument, and then there would be a counter argument that still shows that you cannot go as far as you want. So the story is very subtle, but there seem to be some reasons, some physical obstructions, right, to parametric scale separation. Every time people have come up with examples, they always contain problems of certain type.
Right. I mean, when it comes to the CFT side, I mean, forget about parametric scale separation. We don't even know a scale separated CFT period, right? So,
Well, yeah.
you were saying something?
Yeah. No, I was meaning like, parametric scale separation is a sharply defined concept,
Yes.
whereas numerical scale separation is some sort of it's a vague idea, because is 10 to the 100 a big number? This is not a mathematical
Yes.
question, right? It's more of a depends on the context kind of question. So, yeah.
Sure. Okay. So, when people make vacua which have parametric scale separation, for example, one example is this ADS4 vacuua that you can make out of type 2a, right? And the parametric scale separation is achieved by a flux, right? If the flux becomes bigger, then you get parametric scale separation. And the vacua that they're making are classical. I mean, you don't need quantum mechanical ingredients to, stabilize the vacua because it's type 2a. But then there's type 2b where vacua are so intricately constructed so that you need quantum mechanical effects, and there you don't seem to have this parametric scale separation. So when you say that you don't think that type parametric scale separation is a thing, do you think that the vacua that will be constructed that will have scale separation but not parametric scale separation will have to be made by using quantum mechanical ingredients as well?
It's a good question. Probably, I cannot, rule out a purely classical construction. But the ones that we do have do involve quantum mechanical ingredients. Yeah. So I do suspect that the answer is yes. But I cannot, in this moment, I cannot really
Okay,
conclusively
sure.
say it.
Sure. Okay. So the most famous string theories that people hear about in popular science are these type 1, type 2, A, B, and heterotic string theories, and those are the string theories that have supersymmetry, right? And then there are some other ones that have supersymmetry but they have problems, but that's why we won't talk about them in popular science, like type 0 string theories. But then there are these non-supersymmetric string theories which you have worked on, and they are even more lesser known in popular science, right? So I have several questions regarding those string theories. First of all, how many non-supersymmetric string theories do we know that don't have problems? And by problem, I mean no, they don't have tachyons. And what are the techniques which are different? For example, supersymmetry makes calculations easy, makes things easier. Uh, so is it harder to work on non-supersymmetric string theory? And is it much harder than supersymmetric string theory? And by the way, we can start from how many non-supersymmetric string theories.
All right. So let's say working with this convention that a string theory means a sector of string theory, right? Um, in the simplest class that we can study of these, like weakly coupled corners of string theory are the ones in where space-time is 10-dimensional, right? In particular, completely extended in all 10 dimensions, right? This is the simplest setting to study weakly interacting string theory. And in this context, there are several constructions that have no space-time supersymmetry, right? More precisely, space-time supersymmetry is either absent or broken, right? And of all of these, exactly 3 in 10 dimensions have no tachyons, right? In the perturbative spectrum around flat spacetime. There are other constructions in lower dimensions, which may or may not be connected to the ones in 10 dimensions. How many of them unclear? There are a handful that are known, but I don't think we have a complete classification of those. I would say that the 10-dimensional classification is complete, as far as we know. And yeah, so I spent almost almost the entirety of my research in this topic in these contexts of the stuff that you can do with these 10-dimensional descriptions, which are simpler. So there are these 3 that are particularly simple to study, but still they are much more difficult to deal with relative to the supersymmetric counterparts, for essentially one simple reason, which is that as far as we know, we couldn't find any stable vacuum for any of these. Right? We could find configurations that look metastable, and the lifetime looks long relative to the the relevant cutoff, let's say the string scale of new physics, let's say. So we do have explicit examples of vacuua that we think are long-lived and reliably, under control. The interactions are weak, the curvatures are low relative to the, whatever scales suppress corrections. But even in that case, could there be other processes that make these vacua decay faster than we think? Maybe. So let's say, as far as we can tell, the best we can do with these theories is build metastable vacua that are long-lived. This is the sort of the state of the art. And doing physics in these settings is very difficult because the usual machinery of string perturbation theory that can probe high energy weakly interacting physics is crippled in these contexts because it's very well suited for like flat backgrounds, but these backgrounds are not flat, first of all. Usually they contain some anti-deSitter kind of piece, and more than that, some of these backgrounds do not even exist classically. They involve quantum ingredients, like you said before. They are quantum vacua, as Subdeep Sethi, for example, would say. And doing string perturbation theory proper, so beyond just low energy effective field theory in these, around these backgrounds, is much more difficult because you have to sort of mix classical and quantum pieces in a way that has to propagate order by order in a consistent way. You have to implement something called the Fischler-Susskind mechanism, right? And so everything is much more difficult to do. And not to mention that results that are exact or at least reliable beyond the weakly coupled low curvature regime are extremely hard to come by because space-time supersymmetry allows you to protect many quantities from corrections, and you can trust several dynamical results there. Here, we cannot really trust many dynamical results, many dynamical quantities not to change dramatically as we go to strong coupling, for example. We can trust topological quantities, kinematical quantities like anomalies. So something that we did recently was to check that all the anomalies that we know of cancel in these theories, which is a highly non-trivial check that they can be consistent. Another thing that is lacking, at least not to the degree, not even close to the degree that we have in the supersymmetric case, are string dualities, right? So we have a much, much weaker understanding of dualities in non-supersymmetric strings, or sometimes even whether there are any at all, right? Especially of the strong, weak type, S dualities and such. So there are several efforts, conjectures, ideas, including some of my own, of what these could look like. But the kind of evidence that is available in supersymmetric settings is completely gone. So really, drawing strong conclusions in these settings is extremely difficult. So I would say the best, personally, the highest achievement that we have for me is the explicit construction of apparently metastable long-lived vacua. This is sort of my take on research there so far. Are there any stable vacua? I don't know. I'm starting to suspect that there are no stable vacua unless spacetime supersymmetry is unbroken. So there's that. I do want to say one thing though. So there is this conceptual distinction that sometimes people don't make between supersymmetry in space-time, right, and supersymmetry on the worldsheet, right? And these are two different things. And I want to remark that if you try to formulate conventional quantum field theory using the analogous formalism to the worldsheet, which is the world line of propagating particles, with which you can formulate perturbative quantum field theory. If you want the space-time quantum field theory to have fermions, you kind of need supersymmetry on the world line, even if the space-time doesn't have it, right? And the same works for string theory. So when people say superstrings, what they really mean is that the worldsheet has supersymmetry, so that the space-time can have fermions. It may or may not have fermions, right? But for example, type 0 string theory, right, has worldsheet supersymmetry, but not. It doesn't even have both. It doesn't even have fermions in space-time, and it has tachyons. But okay, maybe it's worth just to conclude this answer to mention that another big development in non-supersymmetric strings recently is, beyond constructions of metastable vacua, is the deeper understanding of the relation between worldsheet supersymmetry, the presence of tachyons in the spectrum, presence of fermions in the spectrum, and how quantities can still be finite, at high energies, despite the absence of space-time supersymmetry, right? So there are some theorems in, at least in some types of strings, like weakly coupled closed strings, for example, where we know that if there are no tachyons, then there are fermions, for example. And we know that the finiteness of quantities like the vacuum energy or anything that involves high energy contributions is not coming from supersymmetry, but is coming from some sort of asymptotic version of it. So even if the spectrum and the interactions are not supersymmetric, bosons and fermions do not match in a sort of a mirror kind of way, they sort of become almost supersymmetric at high energies, right? In a way that makes things finite. And it has nothing to do with the space-time supersymmetry. It's a consequence of the consistency conditions of string theory, modular invariance, for example, stuff like that. So there are these developments, proofs of old conjectures that are very powerful, in my opinion, because they're rather general, and they teach us something deep. Because in a theory of gravity, the spectrum of very high energy states, where these sort of asymptotic bosonic fermionic matching seems to occur, is related to the properties of big black holes, because ultimately very high energy states in gravity correspond to black holes. And indeed, black holes are sort of agnostic to whether the microstate is a boson or a fermion. So it sort of matches this picture, right? So we learn a lot, is what I'm trying to say, but nowhere near as much as in the supersymmetric case.
Sure.
Sorry for the long
No,
answer.
that's fine. I mean, I have a lot of questions regarding this. So, first of all, you said that there are intrinsically quantum backgrounds, in non-supersymmetric strings, and you mentioned, the work of Safseti, who is the advisor of my advisor. So he wrote this paper, I think, with his student in 2022, and so the way I understand it is that when you write down the classical expression not the classical, the tree level expression for the string coupling, it is inversely proportional to a flux, and when that flux goes to zero, the coupling blows up. So is that the sense in which you're saying that these backgrounds don't exist, at the tree level or the
Yeah,
spacetime?
I mean, I think this is a consequence of the more general, let's say, observation that actually I think we discovered. I mean, at least in this context, in 2016, we found these examples, and then Sav also found these other examples. But in all cases, what happens is that there is a quantum contribution to the let's say the potential energy of the dilaton, which enters the various field equations. And if you don't include that piece, which should self-consistently be checked to be the only relevant piece, and then all the others should be suppressed, because if you're ignoring them, they better be suppressed. If you don't include that piece, the solution just doesn't exist at all, right?
Okay.
That's the point. So, and if you include it, right, and then you pretend that you can change the coefficient in front and you can send it to zero, even though you cannot, right? But you pretend you can, then the various quantities blow up, like the string coupling, as you said. So what happens is in these vacuua, at fixed quantum contribution, you have these fluxes, you make them big, and the string coupling is small. But if you fix the flux and you send this quantum contribution to zero, the string coupling actually blows up
Mm-hmm.
and the solution stops existing. Now, again, you cannot actually do this, right? But mathematically, it shows you why the solution doesn't exist unless you put that number in, that contribution in.
I see. So you said that you just said that there was this 2016 paper. Which paper are you referring to?
So this is the paper that spurred my master's thesis work. It's a paper by Sagnotti and Murad, and then the follow-ups by myself and other collaborators on the various properties of these vacuum. And so some of these are classical, right? Some of these are quantum. Depends on the sector of string theory that you look at, the particular type of solution that you look for. Depends, let's say. But the ones over which we have more control relative to the, having explicit examples where there are no tachyons and so on, are of the quantum type.
I see. So another question is that you said that our understanding of dualities when it comes to non-supersymmetric strings is not as good as our understanding when you have supersymmetric theories. But correct me if I'm wrong, but for something like T-duality, you don't need supersymmetry. So I'm sure
That's
you
right.
understand T-duality in the context of non-supersymmetric theories, right?
Yeah. So T-duality works essentially the same way to the extent that you can trust your backgrounds, right?
Mm-hmm.
Because again, we have no stable vacuum, right? So
Right, right.
if you care that everything takes place around some stable vacuum, then no dice. But if you don't care about that, then T-duality works essentially the same way.
I see. And you said that there are, when you talk about 10-dimensional non-supersymmetric strings, string theory sectors, let me use your language. So, which is correct, of course. Then you have these three different, non-supersymmetric theories or sectors. And one of them comes from a projection of type 2b, right? So a question. This is a question that I was thinking about some time ago, and I still don't understand if there is an answer to it. But let me know if you know the answer to this. So we do know that type 2b is T-dual to type 2a, right? If you compactify it on a circle, right? So can you make a similar non-supersymmetric strings from type 2a from using this route?
So I think this has been studied in I think a paper of like from 99, 2000, or maybe 2001. So like rather old paper by Ralph Blumhagen and Anna Maria Font.
Mm-hmm.
So they did, to my understanding, they did exactly what you said. Right?
Okay.
So they and it proved quite fruitful actually, because what happens is that, so let's say you trust that you can do these dualities, right? Um, then what happens is that the main source of problems in this particular construction, which is called the Sugimoto model, right, becomes simpler. So the big problem with the Sugimoto model is that it's a sort of an evil twin of the type 1 string, right? It's an evil twin because this projection includes, basically, it leads to the introduction of a positive energy density that fills all 10 dimensions. It's because there are some anti-denying branes, if people know what these are. And all of this is forced by the internal consistency, cancellation of gauge anomalies, and so on. And so on. And once you have this energy density that fills the space-time, and it also couples to the dilaton in a way that generates a potential that has no minimum, all hell breaks loose because there is no maximally symmetric background, vacuum, anything. So you have to either compactify or look for some non-geometric descriptions, or accept that isometries have to be broken in some way, and everything is terrible basically. But in this T-dual, or hopefully T-dual picture, things are a bit simpler because this energy density that makes our lives miserable becomes localized. And now it still makes our lives miserable, but a bit less miserable. And so those people were able to study the geometry, or the space-time geometry that is produced by these sources of energy density in a way that is more, it's easier to understand, let's say. Now, of course, before that, people studied the geometry produced by this energy density directly in 10 dimensions, directly in the Sugimoto model. These people were Dudas and Murad in 2000 or so. And they did find some solutions that involve some breaking of isometries in space-time. But these solutions have regions of high curvature and/or strong couplings, and they are very difficult to deal with, right, in a reliable way. So there are several works in that direction. So in order to avoid these regions, we have to introduce fluxes and get all the way to these 2016 and onward, solutions that we found. But in these T-dual pictures, things seem to be simpler. Yeah.
Right. Okay. So another question that I have is that so when we study D-Branes in type 2 theories, we study them as something called BPS configurations, right? Because they break some supersymmetry, but not all of it. Can we have D-Branes in non-supersymmetric strings? And is there any essential difference, when you study branes in non-supersymmetric strings?
So yes, we can have D-Branes in these theories, as far as we can tell, of course, given everything I said before. But so everything works essentially the same way. We can study D-Branes from various regimes, much like we can in supersymmetric settings. Namely, You can consider configurations where space-time contains just a small number of branes, right? And then you can ask questions in the language of string amplitudes, right? You can ask what happens to my worldsheet CFT when there are boundary states that corresponds to these D-Branes. And then I have these amplitudes with certain topologies of the worldsheet, yada, yada. And you work out stuff like the forces between the D-Branes. You work out the spectrum of perturbative excitations of open strings on the D-Branes, stuff like that. Then you can look at D-Branes in the opposite regime, namely when you have many D-Branes and they form some sort of soliton configuration that significantly back reacts on spacetime. And you can look at the effective field theory, and you can solve the equations for these configurations. You can see what they look like, what kind of charges they have, what kind of fields they source, right? And you can ask, maybe you can do some mix and match. You can put like a few branes here and a lot of branes here, and then you replace the big stack of branes with the space-time geometry that it produces, and then this brane is subject to this geometry, right? It's a probe, and then you can see whether it feels some force. And then you can ask, does this force have the same character of the force I computed with the string amplitude calculation? So you can do all these sorts of mix and matches. You can also speculate that there are some holographic field theory counterparts to these geometries produced by the branes. I have some works on, in this direction. And even there, you can ask, in this dual field theory description, I have some effective potential if you separate the branes. You can compute it and you can ask, is it repulsive, is it attractive? And then I performed some sort of systematic analysis case by case of all of these things in all these regimes. And whenever the comparison was possible, so the calculation for the same kind of branes setup could be done in different regimes, then it seems like the qualitative behavior was the same. So either the branes are always repelled or always attracted, across these various regimes. And this is a highly non-trivial check because there is no supersymmetry to protect us, right? So this is some stuff you can do. You just cannot trust that all the results extend to all the regimes, right? You just have to do the calculations separately. And of course, one thing that for sure doesn't work is this idea that if you take the same kind of brane and you put them parallel like this, and they have the same charges, then they feel no mutual force, right? This is a consequence of the BPS property that you said. In these non-supersymmetric settings, even if the branes themselves had been BPS without the supersymmetry breaking ingredient, once you include the supersymmetry breaking ingredient in space-time, they do feel a force. And then you can ask, is this force repulsive, right? Or is it sort of a violation of the weak gravity conjecture that some people think should extend to charge the branes, right? Turns out every time you can do the calculation, the answer is that it is repulsive. And it is a very non-trivial check of this weak gravity conjecture for branes idea, right? Because you have no control over the calculation. Either it comes out repulsive or attractive, right? And every time you do this calculation, this is what happens. Maybe the last thing that comes to mind that we found that is very different relative to the supersymmetric case, which is related to this repulsive force, which is also a big difference, is that in supersymmetric cases, if you put a bunch of branes in space-time parallel to each other, they back react, right? And then you go away, you go far away. Let's say if the dimensions of the branes is not too big, right? There is a good notion of being far away, and being far away, space-time becomes more and more flat, right? Because you recover the good vacuum that you had before without branes. Now, in these non-SUSY strings, there is no such vacuum. So what happens when you go far away from the brane? Turns out we found that you cannot get far away from the brain, right? There is a limit to how far away you can get. What happens is that there is some finite length, and how long this is presumably depends on how many brains you put, but it's hard to control precisely. Um, uh, and after this finite length, space-time just closes in something that, from the effective field theory, looks like a singularity. Of course, whatever that is, it's not clear. It's some sort of end of the world, so to speak. We don't know what it is in whatever full theory is, if there is a full theory in this context. So this is a big difference relative to the supersymmetric case. But my point is that it's a big difference in the outcome, not in the methods we use, nor in the kind of questions we ask, right?
Right.
The
Okay.
only thing you cannot use is the supersymmetric protection of things, right? You cannot trust that this result is actually exact. This you cannot do. But other than that, the methods and the kinds of questions we ask is the same. The answers are often different.
Right, right, right. I mean, one thing that I was expecting you to say is that you have to calculate, higher order corrections as well. I think you just said that because you said that the results are not exact, right?
Yeah.
Right. So
Um,
when you said that you have this brain and another brain, and they're not, you're talking about non-supersymmetric theory, the false is repulsive. So you're talking about two brains or a brain and an anti-brain.
I was talking about brains of the same charge with the same sign. So brain rather than brain anti-brain.
So they just behave like charged particles, like they just repel each other.
They just repel each other. Yes, they could have attracted, right?
Mhm.
But they don't. That's the beauty of it.
Okay, I see. So one work that one paper that you had in 2021 that included higher curvature corrections, and that paper was trying to argue that you're trying to have some no-go theorem like result against deSitter space-time using those prime corrections. So can you tell us a bit about that, and does it actually forbid deSitter vacuua in those kind of theories?
So, I mean, so that paper is this paper I wrote with Stefano Lanza. I'm not sure if it involves corrections per se.
I think it says tensions between curvature corrections and deSitter or something like that.
Sorry, this is not the paper with Stefano Lanza. This is the paper with Alessia Platania.
Hmm.
Okay, very good. So this is a completely different paper than what I had in mind. So very good, because I would have given you a completely different answer. So that paper, okay. So what we did in that paper was we attempted to quantify higher curvature corrections in cosmological backgrounds, right? Cosmological string backgrounds. Now, this analysis can, let's say, can only be qualitative at most, because let's say, there's always a price to pay when you say, oh, look, I'm going to compute all order curvature corrections in a way that is not protected by SUSY or something else. So you're making a deal with the devil somewhere, right? And here what we did was we used some methods to compute these corrections, which have some assumption behind, and this assumption behind could be just wrong, right? Um, Now I can explain what this assumption is, but let's say up to this assumption and the approximations that we made in computing these corrections, the upshot is that cosmological backgrounds in cosmological string backgrounds enjoy certain properties that come from T-duality that allow a classification of higher curvature terms in the equations of motion, which is very simple, right? And then once you have this classification, you can, basically it boils down to computing a single function of a single variable. This is this comes from T-duality plus the ansatz of a nice, cosmological background. And then you can ask, what kind of cosmology do you get? Do you get deSitter? Turns out we don't. We found that there is no deSitter solution of this type. And it's important to include curvature corrections when asking about these kinds of deSitter constructions, because without them at the level of two derivative effective field theory, except once you include certain objects with the negative tensions and so on, there are some logo theorems, right, that forbid these solutions. And these noble theorems can be extended to the non-supersymmetric case, where there are extra terms like these potentials that appear. And this was the result of my work with Stefano Lanza, right? This extension of the noble theorem against deSitter at the two derivative level. Now, in this work, we included these higher derivative corrections, and we saw that there's still nothing. But again, these higher derivative corrections were computed with a method that is not fully under control quantitatively, under certain qualitative assumptions that also may be incorrect. But that's what we did. So, nevertheless, it does comply with the result of SETI, which was a worksheet analysis that says basically what should I look for deSitter from the worksheet? Well, it should be some CFT with such and such properties, and then you do some classification, and you see that basically nothing works, at least in certain types of CFTs. And this result of ours, is a bit complementary in the sense that it's a space-time perspective that includes these higher derivative corrections, and it doesn't assume anything in particular about how a strongly curved deSitter would show up in the worksheet CFT. But the counterpoint is that it is less robust than SETI's result, because SETI's result is a CFT result. It's very sharp, whereas the space-time analysis is subject to several ifs, let's say.
Okay, I see. So I see that in your work, with these kind of results, you use functional RG flows a lot. So can you tell the audience that what are functional RG flows? How are they different from normal RG flows, and why are they important in your work?
Well, okay, where do I start? So what is the functional RG? So the functional RG, this is the way I see it, is an implementation, a practical implementation of the theoretical concept of the RG flow that allows you to make some approximations that are not the standard perturbative approximation, right? That they are some different kind of approximation. So, the core concept of what the RG is, the renormalization group, is exactly the same, right? The physics is the same. There's nothing different about that. The implementation is that, the RG flow is sort of a flow in the space of functionals, right? The space of effective actions of some kind. Relative to some scale. Now, there are several types of these, and one can discuss the extent to which the physics of these is different, but the spirit is the same. And in each of these approaches, some of which are more convenient for calculations than others, one can set up an approximation scheme which is not the perturbative expansion, the standard perturbative expansion. So instead of doing, loop counting, Feynman diagrams, and all that stuff, the type of approximation is a truncation of the space of functionals. So much like, well, maybe not super similar, but let's say it's somewhat analogous to the Rayleigh-Ritz method that one can use in certain quantum systems to approximately diagonalize the Hamiltonian, right? You take a finite dimensional subspace of the Hilbert space, and you truncate everything, and you diagonalize, and then you increase the size of this ansatz, right? Tensor networks are another example of this. This is somewhat similar in the sense that one can take a subspace of the space of functionals. In other words, some operators and not others of all possible operators. And then one forcibly projects the RG flow onto that subspace. This loses information in a way that is not systematically controlled, right? It could be that the errors that you make are, not small because you're, for sure, they are not parametrically small in the sense that there is no parameter that you're sending to zero anywhere. Precisely because the whole point of this is not to do perturbation theory in the first place. What you can do is, again, systematically increase the size of this truncation space. But within the truncation space, the RG flow becomes a closed, by force, closed set of differential equations that one can, study. And then one can look for fixed points, one can look for, critical exponents and all that jazz. So the core idea is to truncate to maybe not finite dimensional subspace of functional, but a space of functionals that is under control in some way.
So one more question before I move to another topic. So you said we were talking about cosmological constant, right? And I think you mentioned it earlier that there is no reason, why it should be a constant, right? And I'm sure that you are aware of the recent study that was published that said that probably it's decreasing, right? So that does open a door for models like Quintessence, right? So are you aware that how easy is it to make quintessence models in non-supersymmetric strings, and do you know if people have looked into this?
Well, so yes, I'm aware of these studies, and I think they're very exciting. Now, the extent to which quintessence models can be made to fit easily with these kinds of data is not clear to me because I'm not an expert in this area, but I seem to recall that there are still some non-trivial constraints, right? So people still debate whether you can have the simplest kind of quintessence, right? Or maybe the bounds are too strong on the various parameters that arise in string models. Maybe some people have started looking into cosmological configurations that have sort of that come from rolling down a maximum of a potential instead of a minimum. They have been getting creative. Is my point. But beyond the search for a particularly realistic quintessence model, I would say that quintessence models in general, so without any pretense of realism, have been around in non-SUSY strings since the beginning, more or less. For example, in this paper by Vilas and Murad that I mentioned before, where they were looking for vacuum solutions that include the effect of these potentials that come from SUSY breaking, they also looked at cosmological solutions, right? So they are, and these solutions have a dilaton that changes with time, for example. And it comes from these potentials that are exponentially in the dilaton, right? They have no minimum. And the slope of these potentials is always some quantity of order 1 in the relevant units, Planck units, for example. And this is, to me, to my limited understanding, that's the main problem, right? So the fact that in string theory you cannot just tune parameters as you want, and these slopes and coefficients of these potentials are constrained by some inequalities that we are starting to understand and motivate more and more robustly. And these inequalities, how well do they play with the observational constraints is not completely clear to me. There are some people that study these things in more detail, but of course, I do hope that the simplest kinds of models can be viable. But I suspect that maybe even with the option of going quintessence, we still have some work to do to get a good quintessence. Right?
I see. So we talked about branes, in non-supersymmetric strings. So Can you have something like the Brane world scenario in non-supersymmetric strings as well?
This is a fantastic question because it really leads into what I wanted to talk about for a while. So yeah, the answer is yes, first of all. Now, what kind of brain world scenarios? Well, there are various kinds of brain world scenarios that you can imagine. They may be static, they may be dynamical. Brains can wrap maybe extra dimensions, if any. They may not, and so on. Now, there is a particularly natural type of brainwave scenario that occurs in these non-SUSY strings that I've been studying. Natural in the sense that it's really sort of the simplest thing you can imagine, and you are naturally led to this kind of scenario. And how does this work? Personally, I got into this story back into, I think, 2018 or so, because I was led to it by the study of the dynamical properties of these metastable vacua, right? So what happens in these vacua is that the first thing you have to check is that if you give a little kick to the configuration, the perturbations do not blow up, right? There are no tachyons in the sense. And this we can make sure of in certain cases, and we have at least one explicit example where this is true. Even if this is true and the vacuum is metastable, it will decay by tunneling, as Coleman, De Lucia, Callan, etc. taught us back in the day, even in gravity. And it nucleates by, well, there can be several types of tunneling process, and the one that we understand the best is the nucleation of bubbles. They are bubbles where the inside spacetime has a lower energy than the outside. And we understood in these particular string, explicit string constructions, that in this case, these bubbles are just D-Branes or NS5 branes or other kinds of branes. And the reason why the energy inside is smaller is that the difference is carried by the tension, and the difference in flux that supports the vacuum is the charge of the brane itself, right?
Do
This
you mean
is,
energy or energy density?
well, both, because the energy is the energy density times the volume of the bubble.
Sure. Okay, I see.
I mean, of course, you can because the outside has infinite volume on any Cauchy slice, then you can say, oh, but what's the energy then?
Mm-hmm.
Yeah. The proper quantity is the energy density to consider.
Mm-hmm. Okay.
And these bubbles expand, right? They are driven by the tension and the charge and so on. And the reason why they expand is exactly the same reason why branes of that type repel each other, right? So this weak gravity kind of bound plays the role every time. It tells you that they repel. It tells you that they can nucleate, so the probability is non-zero. And it tells you that once they do nucleate, they expand instead of collapsing. So this is why it's a very nice scenario to look at, because we are led to it. You look at the simplest kind of non-supersymmetric string, where supersymmetry is in spacetime is completely absent, or maybe it's broken at the string scale. The simplest kind of setting from the point of view of string theory, 10 dimensions, okay? You look at configurations that are as stable as possible. You find metastable vacua, and look at that, they nucleate these branes and they give you these bubbles that expand. And now what do you do with these bubbles that expand? You can ask, what is the physics that a little observer living on the bubble would see? Turns out they would see deSitter cosmology.
Right.
And and the physics of this deSitter cosmology can be separated from the physics of the ambient space-time with the separation of scales I was talking about, if if some condition is satisfied, basically the charge and tension of the brane, they have to be very close, right? So the ratio cannot be exactly 1, that would be an extremal brane and it wouldn't nucleate, but it has to be close to 1, right? And we found a model in which this happens. And coincidentally, in this model, the cosmology lives in 4 dimensions, which is nice. Didn't have to happen, but it does. So at the end of the day, we have this model where we have, let's say, either a deSitter or a quasi-deSitter cosmology, depends on this particular construction. And either you have a cosmological constant or you have something that changes logarithmically slowly, right? So very slowly. So I call it quasi-deSitter. But either way, you have a nice 4-dimensional cosmology with everything you would like. You have gauge groups that look like the standard model. You have chiral fermions, gauge fields, scalar fields, everything you like, because all these things live on the brane, right? The only thing you have to ask is, how does gravity look like in these brane worlds? And there is a lot of work that has been done by the group in Uppsala in Sweden, by Ulf Danielsson and collaborators, actually including myself, and some people here in Munich. And we tried to understand how gravity is seen by these low energy observers, because this construction, and this is a very important point in my opinion, is not an effective field theory in 4 dimensions, right? It's a brane world that is not an EFT. So there is no effective Lagrangian in 4 dimensions that you can write, right? There is no, the Einstein equations that govern gravity on this brane world are sort of induced by the ambient space-time gravity. They are not, real Einstein equations, so to speak. And there is a lot of debate going on there, but let's say at least some aspects of this gravity on the brane work as you want them to work. Even though this is not an EFT, these equations look like the ones of an EFT. They look like fields on the brane coupled to some gravity, effective gravity, that looks like Einstein gravity, right? So this is the situation more or less up to published literature. And it's very exciting because maybe you can circumvent the whole needle in a haystack problem of looking for realistic EFTs in the string landscape, which without supersymmetry is a nightmare, right? Even with, to be honest. So it's really a nightmare, and so it is the possibility that maybe we can just look for an alternative model to which we are led naturally by supersymmetry breaking is very exciting, right? In particular, since it gets all these things right, cosmology and the kind of gauge theories that you get and so on, separation of scales and everything. Now, it would be perhaps a bit disappointing from a more philosophical point of view, if you will, if you think that the fact, or at least the expectation, that string theory produces a finite number of EFTs, it's a very, desirable thing for some reason, because otherwise the number of EFTs that you can write down is continuously infinite. So, but still, this possibility is exciting for an alternative paradigm for string phenomenology, right? And again, the basic checks that this thing works have been performed. So even if it's not an EFT, it quacks like an EFT in some aspects. So we saw that Maxwell fields gravitate as they should. They couple to this effective gravity on the brane, which is not real gravity, but it's an induced gravity from the ambient space-time. These couplings are correct, at least to low energies. Then there are deviations, as expected. Gravitational waves make sense. More or less everything seems to work. except that there are reasons to believe that some things work differently than in effective field theory. So these models are not EFTs. They quack like EFTs, but not always. So we are now looking into deviations between this Brane world scenario and EFTs that are, immediately there. They are not suppressed at low energies. They are there to leading order. And we are looking into these differences to see if indeed to model the real world accurately, you need a bona fide quantum effective Ethereum for dimensions, right, at low energies. Or if you can get away with some Brane world of this type, which is not a 4D EFT, although it lives inside, let's say, a 10D EFT in this case. And so this is, let's say, unpublished stuff. We don't know if this is true, but let's say we checked a billion gauge fields. We haven't checked, let's say, how massive matter on the Brane gravitates. It could be that it does not follow Newton's law. What does follow Newton's law is not localized matter, but extended matter away from the Brane. But then it turns out that this kind of matter is too heavy to give particles, light particles of the standard model. So does localized matter on the Brane gravitate according to Newton's law at long distances? We have to check. Do non-abelian gauge fields couple to this induced gravity in the way that they do in the standard model? Standard model intended in the modern sense as this effective field theory, including gravity and everything. Maybe it doesn't, right? And if it doesn't, is it a deal breaker for these models, right? Because, technically we haven't really, done the Cavendish experiment with gluons, like or W bosons or blue holes, whatever. So it's not like we can say immediately, haha, so this model cannot be realistic because it's not an EFT and there's this difference with respect to EFT. So the differences that we expect to be there at leading order at low energies are very subtle, right? From the point of view of phenomenology. Like I went to an experimentalist and I asked, how far are we from doing the Cavendish experiment with two Z bosons? Like, he didn't laugh in my face, but we laughed together. So we are looking for let's say, quantities in this Brane scenario that are sensitive to this difference with respect to EFT in a way that can be accessed experimentally, like with current technology, or maybe already has been. For example, if non-abelian gauge fields gravitate in a different way, we should see this maybe in the primordial universe, right? In the signatures that quark gluon plasma left in the cosmic expansion or something. So we have some reasons to believe that the cosmology would be too different relative to what we see, whereas the cosmology predicted by EFT works. We are looking into it, basically. So, I'm sort of growing more skeptical of this non-EFT kind of string phenomenology. But, science is about finding the answer, so we see what we see.
Sure, okay. So there's one more question, and then I have some questions about being a physicist, and then I have some questions from the people before we end this.
Fantastic.
Yes, so that's something that I do in every episode. So one question is that, so probably the first part of this question, well, I think it's one question. So one topic in this question is not directly relevant to your work, but your work is relevant to non-SUSY strings. That's why I'm asking this. So do you know that if people have tried to write down string field theories for non-supersymmetric strings?
So as far as I know, no. But I did speak with an expert in this field, which is Monkey Kim. Mm-hmm. And we were chatting about these possibilities. There seem to be no obstructions to doing this. It's just very technically difficult. And one of the reasons why it's difficult is that one needs to implement this Fischler-Susskind mechanism of, consistently repackaging each order of the perturbative expansion around backgrounds that are not, they're not good backgrounds. They have to be deformed, and so one has to, shift the background order by order, and this is difficult. But I don't see any obstruction of principle, and it would be very interesting to do, because string field theory is a good machinery to do this kind of thing.
Right. Okay. So one question that I have is that as a physics researcher, we want to pursue our program or different research programs, and we want to continue working on that. But how do you try to balance that urge as a physicist with the pressures from maintaining your metrics, right? Like publication numbers and citations and these kind of things. So that's a question relevant for a lot of researchers, as you can imagine. So do you have any
Absolutely.
advice?
Yeah, well, I can tell you my personal experience. So, I come from sort of a background where the philosophy is not to, it's to prefer quality over quantity, first of all.
Yeah.
So, I mean, I am not able to do that all the time, right? There are some occasions where I am sort of forced to, maybe to rush a little bit here and there, some projects, mostly when it involves deadlines for collaborators, especially younger ones, because, maybe that one publication would have landed them, job security for the next 2 or 3 years. Like, it's a big deal, and it's very hard to balance these things. So I try to do my best to prioritize quality, first of all. Quality as in the questions to ask are physically meaningful and deep, and not just academic exercises, right? Um, and take proper time to check and double check and triple check everything, and make sure that things that are being written and put out are at the very least properly weighed. If there is an open question, it's an open question, it's fine. It's important to be transparent about the extent to which the question is open. How likely do we think that the answer is whatever it is, and why, right? To me, the transparency is super important beyond this pressure. So I think it's relatively easy to, I mean, insofar as one has a feeling for what questions are deep and important, to focus on those questions. It is much harder once you do work on these questions not to rush publications sometimes because of these deadlines and so on. So I do think that a little bit of leeway there is sort of necessary to survive. But we should keep in mind that the standard that we should aim for is to work slowly, carefully, and prioritize the science over the social aspects of, like, getting grants and positions and so on. In an ideal world, of course.
Right.
But the personal experience that I was gonna mention is very ironic, in some sense, to me, because I started out very anxious about all these things. I started out being super worried about my low citation count, and oh no, my colleague has more papers and this and that. And everybody tells you, oh, as you go on, it's gonna get worse, right? Because you're going to have to apply to more places, and there are bottlenecks. The postdoc market is crazy, and it gets crazier every year. Yeah, this is all true, right?
Yes.
I applied this fall. I got 0 postdoc offers. I have
That makes
some,
me so scary. That you got zero
right?
postdoc offers.
Well, thank you for the subtext there, but yes,
Yes.
um, I have some longer term, bigger applications. coming out. And I had people tell me like, "Oh, I would hire you if I had the money," right?
Okay.
They just didn't have the money. So it's a problem. Nevertheless, I find myself worrying about this stuff less and less. Like I'm less and less anxious about it the older I get. Maybe it's a positive side effect of aging. But somehow, counter to all expectations I had, and counter to everything that people told me, and still do, I care about these metrics way less than I used to. Like, do I have a lower citation than my, next door colleague? Yes. Do I care? No. Somehow, sure, I will check from time to time, but
Yeah. I mean, don't you think that citations depend on the field that you work on,
oh yeah, absolutely, absolutely.
right?
If you if you work on in a niche field, it's gonna, you're gonna get cited less, of course. But still somehow you cannot expect people who are on hiring committees to know, oh, this field is super niche, blah blah. Like, you hope that these people know the science of what you're doing, and whether it's physically deep or important, and this and that,
Mhm.
how good the work, the substance of the work is. But maybe they don't. I mean, maybe sometimes they do, sometimes they don't. I have absolutely no clue. And maybe some systems just blindly look at these metrics, putting a bunch of fields together in theoretical physics, hep-th, or whatever. And I know of some systems that surely do this, at least in the starting stages of the hiring process. Even in Italy, right, there are some barriers, some hard barriers to some type of applications that you can do for
Mhm.
professorships that just need you to pass that threshold, whatever you work on, within a sector, within some bureaucratically defined sectors that
Yeah.
may or
Yeah.
may not reflect the actual status of the research that's being carried out. So it's a mess. It's a mess that I find myself caring less and less about. Maybe it will come back to bite me, this uh, this carelessness. But I mean, of course, when I do apply to positions, I do put effort into it. But I try not to stress over it too much once I send everything in. Once it's out of my control, just like I don't care. I just want to do my research. I want to think about stuff and then be happy.
Yeah, sure. I mean, in this context, suppose that there is some PhD student in high energy physics who has like 3 papers in PhD. Do you think that student should be worried all the time that, oh, won't get postdocs?
No, I mean, I completely understand that they will probably be worried, right?
Hmm.
I would be worried too in that situation. But should they be worried? Probably not. I mean, I think if the work is good, like there are many, people who hire postdocs, for example. Sure, maybe some committees contain people who don't know about the science and care about the metrics. I actually don't know, right? But maybe they do. But not everybody, right? I mean, there are some actual serious scientists that read your applications. And you may even have 0 papers, but if you gave a talk over there and it was brilliant, or maybe you have 2 papers and they're great, maybe not even published, right? I mean, Jake McNamara, for example, has some papers that I don't even think are published in journals, and yet they are extremely cited and well known, and they are groundbreaking papers.
Yep.
And of course, this is an exceptional example, but what I'm trying to say is that I think people in the hiring committees that are worth, whose opinion is worth caring about, will care about the content of your research, not the amount, right? So hopefully, if the research is good, right? And or you do some you put some effort into networking, then it will be good.
I mean, there is an example that that give me some, I don't know what's the word to use here, some solace, but that example is from such a different time, so I think that's not relevant. I don't know if you know this, but do you know that Polchinski had 0 papers in PhD?
Yes, I know, and I know that. Okay, I have some recollection of something along the lines of him faking his way to a postdoc,
Okay,
right? Could it be that like he basically, he faked it till he made it, like just took an office and just stayed there, and people
sure.
just thought, maybe I'm wrong on this. I think I read it somewhere, but nevertheless, even with just the 0 papers thing,
Yeah.
this is incredibly like comforting to me to think about
Yes.
every time. I often, quote this and think about this because it really shows, right? That I think also Bekenstein had maybe
Yes.
one paper, four
Yes.
page paper, something like that,
Oh yeah.
which
I
was
mean,
groundbreaking, obviously.
I think Britain had only 2 or 3 papers, right?
Yeah, I
But the
mean,
thing is that it was a different time. Is it even relevant?
yes,
I don't know.
yes, yeah, no, I agree with you. I agree with you. But still, it brings some sort of solace, as you said. And
Mhm.
I truly, let's say, I want to believe, right, that the worthwhile people in hiring committees will care about your work. And even regardless of that, I think putting effort into networking really goes a long way beyond how many papers you have. It's really important to make oneself known, right? Like to go out and self-invite to give talks to,
Mhm.
in places, and people will often just welcome you there. I mean, especially if they're not paying for you, right? They will just say, ah, yeah, whatever, come give a talk, and we'll chat. That's cool. And then you say, hey, look, I'm interested in applying here, and they will say, okay, great, good to know.
Sure.
And if you meet at conferences, you go there, give talks, and so on. Maybe you exchange some emails. This really goes a long way
Okay.
to help.
I mean, there is one thing that I have noticed. I don't know if this is something that other people have noticed as well. Um, if you look at the careers of senior scientists who have, I mean, I'm not talking about Wittens and Sens. I mean, they're just exceptional. But like, people who have had good careers as a physicist. If you look at the number of papers they published each year, it always comes out to be 4 or 5. Have you noticed this thing?
Yeah, I think I was, I would have guessed as much, more or less. Yeah.
Okay, I see. So I think if there's a student who has like 4 or 5 papers each year, that student should be fine, right?
Well, I would say doing a PhD, getting
Yeah.
that kind of number should
No,
be
no, not in
actually
PhD.
poor.
After PhD. In
Ah,
PhD, it's
sorry,
fantastic,
sorry. Yeah, 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 yeah. I know. I agree. Yeah, no, of course, of course.
right? But related to PhD, my second question, my next question was about that. Uh, in your opinion, I mean, until now you're a postdoc, but I'm sure you'll be a professor one day. I hope so.
I hope
Uh,
so. Thank you.
Sure. So, um, in your opinion, what are the qualities of a good research advisor?
Advisor. Okay. Well, I mean, I have my own experience as an advisor for several master students and one PhD student at the moment. But let's say I have my approach, and I feel like it's good. Otherwise, I wouldn't be, following it. But I don't actually know if it's truly the right thing to do. What I think is a good approach for now is, being available for, you know teaching, the science of it, and the 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 trappings of the market and how things work, conferences, applications, and this and that, being there. Okay. But also not like, so guiding as in suggesting what to do, and especially why to do whatever it is that we're doing. Like I think motivating things is extremely important, because otherwise students especially, can get alienated with, why am I doing this abstract nonsense, right? Like what am I actually trying to achieve here? Am I actually trying to understand the world we live in, how, why, etc.? So I think this is very important to lay some conceptual groundwork for what we're doing and why, and to always remind them that, if this alienates you, there is a life out there, and with your qualifications you can probably get places and get paid much more than I am right now. So it's not the end of the world if you don't get a position or something. And then research wise, yes, guiding, but I feel like some supervisors are maybe a bit too strong in the guiding part, as in, do this, period, right? Whereas I try to give a more open perspective on, like, oh, these are some cool problems that people think about for this and this reason. What do you like? What kind of things do you like working on? And of course, there has to be a compromise between relevance for the community and timeliness and personal taste. Um, but these are things that can be discussed together, right?
Mm-hmm.
So it's not like, I don't think the advisor is a parent or anything. It's a work relationship that can be very relaxed, very easygoing, but professional. And the guidance, I would say, shouldn't be too focused, right? It's important for a PhD student to specialize, to find their niche, at least a niche to start from, and then broaden up. But I don't think they should be confined to it, lest otherwise they come out with, with
Blinders.
yeah, blinders, exactly, like monochromatic vision or some other metaphor of this type. Like,
Mm-hmm.
I often find some PhD students a bit, one-dimensional in their expertise sometimes. Well, actually, to be fair, even some senior researchers, for that
Yes.
matter. So I think it's important to be broader, not just because being one-dimensional is not okay. I mean, it's totally fine, but in fact, to make groundbreaking discoveries, it's important to be extremely expert in one thing. But I find a correlation, like an empirical correlation, between how broad the expertise and understanding of a researcher is, and the probability of them finding an actual breakthrough, right? Because being broad allows you to ask original questions, allows you to find original approaches, right, in directions that more focused and technical people have tackled in the same way for decades, maybe. So I think it's important to be a bit broader and have a conceptual understanding of what we're doing, with technical prowess for sure, but at least some conceptual basis. Like, what are we doing? Why? What is the context in which what I'm doing is situated? All that. So I think that's important, and I always try to emphasize this with the right level of focus.
I mean, I understand what you're saying, and I mean, I agree with it, with almost all of it. But I understand that you're not. Um, okay, are you aware of this essay by Freeman Dyson, which is called "Birds versus Frogs"?
No.
So he says that birds are kind of researchers who know about a lot of things, but they don't know the details of a particular thing. And frogs are like who know the details of a particular thing very, very well, but they don't know a lot about, many other things. So what you were saying, are you saying that it's better to be a bird to make a breakthrough, something like that?
No, I'm saying that because the space of topics we research is very sort of multidimensional, topics, technical approaches, and so on. I think in some directions, there's a distribution of frogness and birdness. that is more nuanced than that. That's what I'm saying. And I think there should be some degree of birdness and some degree of frogness distributed in certain topics in a way that is very difficult to nail down and balance, but it comes with time. I just think it's not good to just go for one extreme
Mm-hmm.
by fiat, by principle. I think it's good to sort of think about a bit being a bit of a bird always, like never be completely frog. Let's say
Mm-hmm.
this is what I would say, and then see what happens because research is extremely nonlinear as an activity. Something that you read 15 years ago in some other topic suddenly becomes essential in whatever you're doing that otherwise would have seemed completely
Right.
orthogonal.
There is this theorem, probably you are aware of it. It's called Schenker's theorem. It's called that. The theorem says that the topic that you dislike the most will be relevant for your next research project.
Like I lost count of the times that this happened to me.
Yeah, I can imagine. So there is one more question, then we can go to people's questions. So this was the question that I asked you earlier was about advisors, but there is one question from the perspective of students. So when you are, an undergrad, or if you are, a master's student, and you're not doing your thesis, it's taught masters. The mentality that the student is in, and in those particular programs, is to solve exercises, right? And okay, when you're an undergrad, the exercises may take a day at most. When you're a master student, there are some problems. For example, if you are solving the problems of Peskin and Schroeder, for example, some of them can take more than a day. I mean, much more than a day, right? But then when you're doing research, the problems can take years to solve. So how do you make this transition in your mentality? Is there any set way to do that?
Oof, that's a big one. Let's say so. Because I was always very curious as a kid and teenager and early adult. I somehow always found myself with the research mentality sort of built in, right? So I never actually struggled by pure luck. I never struggled to get myself into that mentality. And then when it came to exams and problem sets and so on, which, as you said, became increasingly time intensive, what helped me there was just the competitive side of my personality, like this idea that I have a challenge, I have to finish the challenge. Period. Like there's no alternative in my head, and so it just that gives me the drive to solve problems, right? So yeah, that's the way I sort of, it was more than a single transition, it was a double transition, because I
Yeah.
start out thinking about the big questions and this and that, and then I go into this, the university years and PhD and so on, where you grind your way through extremely important problem solving work, and then you sort of come out the other side and say, oh, look, I can think about things in a research way again,
Hmm.
in a more mature way, of course, understanding all more and more the subtleties of it, and be more aware of how things actually work. But still, I think the philosophical nugget was always there. So how would someone who doesn't know about this idea of research to start from, dealing with that transition? This I don't know, but I think a good advisor should help with that. Should try to, you know, to delineate the difference between studying what is settled, well understood, and going out and doing research.
Well, I think one thing that I was trying to ask about when I asked this question was that suppose that you are solving an exercise from a book, right? And suppose that okay, as an undergrad, right? And suppose that, okay, you were not able to solve that in a day or two. You would know that, okay, there's some way to solve this, but I can't see it right now because if it was that hard to solve, they wouldn't include that in the book, right? But that's different from with research. You don't know, right? How much time is required.
It's completely different, of course.
Yes. So a lot of people start doubting themselves when they make this transition and say that, okay, probably I'm not good for research because it's taking so long, right?
Okay, I understand.
Yeah, that kind of transition, how do you tell yourself that, okay, this is normal? This is not, it's not that you're stupid or something like that.
Okay, now I think I understand what you meant to ask, and it's a much more important question. And so a lot of almost everybody I know goes through this kind of maybe imposter syndrome, so to speak, and myself included. And I think the a good way to go about it is go through it together, collaboratively, like to remind ourselves, not just to ourselves, but to each other, that this is a thing that happens, and that nobody solved whatever research question you're struggling with before. And so it's not like, sure, maybe you can't solve it, but neither can anybody else, so it doesn't make you inferior in any way. And if you are worth, like, if your research is good, like the physics is substantial, people will notice, right? Like, and so it's good to remind ourselves both that these are problems that never anybody has ever solved before, and also that we're doing this for a reason, right? We're doing this for a science reason, which is understanding the world, and we're doing this because we love it, right? Has to be something we love doing. Otherwise, I would go in some tech company and earn a gazillion euros a second. So these are the things we should remind each other and ourselves about constantly, and that's what I try to do with my students, my colleagues, my friends. I think it's much healthier than this more cynical attitude where nobody ever admits that they're wrong, or that they don't know something, and it's always a contest. I think it's more healthy not to do that. Also because if you would have won the contest, people would have noticed anyway, because if your research is good, it's good.
Sure. Okay. So let me ask you some questions that came from the people. So when I announced this podcast, some people asked me some questions to ask you. So one
Great.
question is that by seeing today's conditions as a theoretical physicist, should we also have a backup plan as an academic?
Oof, that's a good question. So I think I will go 50-50 between not having anything at all, because this is what I want to do and this is what I will do, and having a good backup plan. I will apply to this and that, and see. I think personally I'm in the middle, right? Like I am confident, reasonably confident, that I will stay in academia. But if push comes to shove, and I can't, then I will go into maybe the tech industry or something. But it's a vague idea. It's not a concrete step-by-step plan. I think if you have no plan whatsoever, maybe it can give you some anxiety, right? Because, oh, what if I don't make it? And if you have a fully detailed plan, it's kind of like having one foot out the door and being like, maybe you're not fully committed to the actual job that we're trying to do, which I think is a very noble endeavor, for humanity to pursue. So I found myself in the middle, let's say, and I think it's still safe, because essentially everybody I know who left academia with our credentials didn't really have a concrete plan, and also didn't have a hard time finding a good job. So
You think
it's
that
not
they
like
didn't?
they planned their exit.
So they didn't have a hard time finding jobs? That's what you're
No,
saying?
it was rather easy.
Okay.
Maybe not a cakewalk for everybody, but rather easy, I would say, considering what I would have expected, let's say. So it's, I mean, because these are extremely smart people, right? So it's not like, yeah. So
Yes.
I think it's okay to have a vague idea of an alternative, but not like plan to everything to the detail.
Okay. So another question is that recently Vafa and his group discovered a new non-supersymmetric string theory. Is the search of non-supersymmetric string theories a topic of current research? Is it expected that new ones be discovered in the near future? I think we kind of discussed this question, but do you want to add something?
Yeah, I mean, just to summarize, there are other constructions of this type that have been found, and but I don't think that a systematic search has been completed by any stretch. So I would expect to find more. I don't see why not at the moment, and it would be exciting to see if there are any patterns there for sure.
So this theory that Vafa and his group found, is that a theory in 10 dimensions?
No, they are lower dimensional
Mhm.
theories, let's call them, that happen to have no tachyons. They have several nice properties that sort of mirror what happens in 10 dimensions.
Okay.
And so I expect much of, maybe not everything, but much of what I said before about the 10-dimensional settings to apply to these as well.
Okay. So the next question is that he wrote a paper with people in asymptotic safety about swampland. What can we learn about gravity from asymptotic safety according to him?
Well, so here I'm gonna give an answer that is, my take, not my collaborators' take.
Sure.
So but so actually I gave a talk about this. I think last week,
Yeah.
recently, and it's gonna appear on YouTube for interested people. And so I did this work because I'm interested in quantum gravity, and I'm interested in. I mean, I want to know if there is any value or in ideas that popped up in all kinds of communities, because I'm interested in whether string theory is the only option or not, right?
Mhm.
And so I looked very deep into asymptotic safety as a scenario for gravity. And my personal take, again, my personal take is that it doesn't work because of problems with with black hole physics and holography and other physical principles and ideas that are very general, very broad, and we expect. I mean, to me, there are good reasons to expect that these things are there, like black holes have microstates, holography is real,
Mhm.
and stuff like that. And all of that really is incompatible with the asymptotic safety scenario. Now, whether one can turn around this logic and say, oh, maybe black holes don't have microstates, maybe holography is not real, this and that, then this opens up. So to answer the question, what can we learn? We can learn what questions to ask also in other approaches. So for people in string theory, we can learn more about string universality, like why do we think that string theory is the only option for quantum gravity? What are the supporting motivations behind this? What are the connections between these motivations, and is there sort of an irreducible primitive set of ideas that these motivations come from? How robust the arguments are? All of that we can learn by examining other approaches. For people working in other approaches, they can learn what kind of questions to investigate based on there is this tension with black hole microstates. Great. Then let's how can we circumvent this tension if our idea works, or if we can't circumvent it, maybe the idea doesn't work, right? And we can move on. So I think it's helpful for both sides to learn not maybe about quantum gravity proper, but how to proceed in learning about quantum gravity.
I see. I mean, another guest on this podcast who is, much senior than both of us, I mean, had said similar things about asymptotic safety. I'm probably about, John Donahue.
Yes, I know him.
Right. So John Donahue, I think he had other reasons to criticize, asymptotic safety, but he said something along the same line. So I'm not surprised that you were saying the same thing now. Okay. By the way, I had one question that I should have asked earlier, and then I can ask the last question from the people. So when we were talking about branes in non-supersymmetric strings, we know that in the mid 90s there was this calculation by Vafa and Strominger to explain the black hole entropy. Can we do a similar calculation with branes and non-supersymmetric strings?
Well, so the short answer is no.
Okay.
Let's say not yet. Not to the extent of reliability of the Strominger Vafa and similar calculations. The slightly longer answer is that some people have tried, bouncing between the supersymmetric calculations and some non-supersymmetric black hole constructions via some dualities. For example, Ricardo Argurio back in, I think in even his PhD thesis has some developed some ideas to that extent. Now these ideas are circumstantial and not fully trustable because otherwise everybody would know about this. Right? But so this is the slightly longer version why the answer is no for now.
Okay, sure.
So
Okay,
yeah.
so you recently worked on the fact that we have the swampland conjecture that there are known global symmetries, right, in quantum gravity, and there you talked about the breaking of generalized global symmetries. So this question is about that. So the question from the people say that in the no global symmetry conjecture, people rule out the -1 form symmetries, saying that there should be no free parameters in quantum gravity. But if the -1 form symmetry is discrete, you don't necessarily have a parameter in that case.
Well, you mean a continuous parameter or?
I mean, I think so. I mean, I didn't write that question, but yeah, I think so.
Yeah, no, I agree.
Okay, you agree. Okay, sure.
I would say. I mean,
Hmm.
sorry. I think the idea that -1 form symmetries are absent is very cool, very enticing, and it does arise in string theory. I think we have less motivations for it
Hmm.
because they are not actually symmetries, right? So I really would like to understand this better. Like for example, Guri is trying to frame this question in the context of CFT, from ADS CFT kind of perspectives, and to really understand whether this is true. Right? If parameters are only marginal deformations of the CFT, which therefore have a bulk dynamical field and so on. So it's a really cool question, but I don't really know how to make progress in that direction.
Okay. So I think my questions are over. Thank you so much for your time. And I hope that we can have a chat in the future as well. So
I
thank you.
would be stoked. As I said, I really admire the work you're doing here, and I'm
Thank you.
super happy to chat whenever in any capacity.
Thank you. Have a good day. So if you like this video, give it a thumbs up and consider subscribing. And the YouTube algorithm thinks that you will also like this video.